In this screencast, we're going to go over the second method for performing hypothesis tests on the mean, and this involves using p-values. P-values are not just used for hypothesis testing on the mean, but we'll use them for lots of other statistics as well. Recall from the previous screencast, there are two techniques for performing hypothesis tests. The first one that we covered in that previous screencast was using confidence intervals and confidence bounds. This technique is not typically done too much anymore because it's really easy these days to calculate things known as p-values because of our computing tools that are readily available to us. So in this screencast, I'm going to go over using p-values to perform hypothesis tests. First of all, what is a p-value? The book definition says that the p-value is the smallest level of significance that would lead to rejection of the null hypothesis with the given data. This is in fact a good definition, especially if you are experienced with statistics, but unfortunately, while you're learning what a p-value is, this oftentimes leads to a little bit of confusion. Another way to think of it, a p-value is the area in the tail, or tails for a two-tailed test, when a test statistic is compared to the sampling distribution based on the null hypothesis. And I hope to make this more clear in this screencast. Let's revisit an example that we've been talking about in the last couple of screencasts. You really like to ride bumper cars. They claim that the rides last 3 minutes, but you think that the rides last significantly less than 3 minutes. You also know that the variance is known, it's 0.05. We can set up a hypothesis test. The null hypothesis, the mean is equal to 3. Alternate hypothesis, mean is less than 3. We can collect sample statistics. In this case, my average is a little bit different. I'm using 2.80. If we had an alpha, a risk level of 0.10, and based upon a confidence bound, the confidence bound approach, will we accept the alternate hypothesis? Recall that for a lower tailed test, we can set up a confidence interval, x bar, greater than mu minus z alpha times sigma over root n, and we're going to reject the alternate if the sample average is contained within that confidence bound. And we have similar criteria for an upper-tailed and a two-tailed test. We can create this upper bound on the sample average. We can substitute in our mean of 3, z of 0.10 is 1.28, and we can substitute in our standard deviation and our sample size, and what we end up with is a 90% confidence bound on the sample average if the true mean is 3, is x bar is 2.872. That means that we're 90% that a sample average will be 2.872 or above, as shown in the shaded region. Our sample average, we're getting a sample average of 2.80. 2.80 is not in that 90% confidence bound. 2.80 lies somewhere down in here. And therefore, our conclusion is that that would be rare if alpha equals 0.10, and we would accept the alternate hypothesis. If we did the same thing, the same analysis for alpha equals 0.05, so what we're doing is we're reducing our risk level incrementally, so we're slowly reducing the risk level. If we plugged in alpha 0.05 and did the same analysis, we would define a 95% confidence interval, and that limit is 2.836. That means 95% of the time, a sample average, if the true mean is 3, will be to the right of 2.836. What's our sample average? Well, we got 2.8, and so 2.8 again, if alpha is 0.05, we would assume that that's rare. Our conclusion would be to accept the alternate, and we would reject the null hypothesis. In this way, we can keep decreasing alpha until we're right at the border of accepting and rejecting the alternate hypothesis. Let's go through one more example. If alpha equals 0.02 and we perform the analysis, a 98% confidence interval, we would say, is any sample average greater than 2.795, which is right there. We're 98% confident that the sample average, if the true mean is 3, will lie to the right of 2.795. Well, what is our sample average? Our sample average is 2.80. 2.80 is just to the right, just inside of our 98% confidence interval. And so in this case, we're right at the boundary between accepting and rejecting the alternate hypothesis. And in this case, we're just inside, so we're going to reject the alternate. Now, if you keep fine-tuning alpha and you keep adjusting alpha so you're right at the border of rejecting and accepting the alternate hypothesis, that is the p-value. The alpha value at which that occurs is the p-value. And this is what the book's definition is trying to get at. The p-value is the smallest level of significance that would lead to rejection of the null hypothesis with the given data. In our case, our p-value then is about 0.02. And in fact, you'll see later on when we do this in Excel, the p-value is closer to 0.225. So if we get a better estimate, it'd be 0.0225.